Okay, here we have a question about refraction. Okay, as ever, take your time to have a look, and when you're ready to see an explanation, press play. Okay, so it's kind of interesting one. This is about sound. We usually think about refraction in terms of light. I did notice in one of the paper 2s that there was a question about critical angles of sound. Okay, so IB is clearly quite interested in that idea, so absolutely take note of that. Let's have a look at the question and go from there. We know that the sound wave is directed towards a boundary and part of it is refracted. Okay, so I'm just going to put up this image. Now, whether this is right or wrong for sound waves, I mean, I think it's just a generic picture for refraction, but it answers our question. Anytime we have refraction is the change in the direction due to a change of speed. Now, you'll notice in this case, if we're changing our speed, then our wavelength is going to change. The wavelength must change accordingly. And so therefore, our statement 1 is absolutely correct. Doesn't matter if it's speeding up, slowing down, the wavelength changes in refraction. So we are going to get rid of option C here because it says that this is not correct. Okay, now, key point here, and I like this diagram because it shows that actually when refraction happens, often two things happen. We have refraction partially here, and then we have some reflection. Now let's think about what that means in terms of energy. What this means is we are going to lose some energy, and therefore the amplitude is going to change. The amplitudes of these two signals must add up to make the same thing. And so therefore if I've got total in, some of it's going this way, some of it's going out, that means the amplitude must also be different, which means that we can get rid of B because that's the 2 is not true. The last bit is really just a bit of brute force and something to remember. Something to remember here is that the frequency stays the same in refraction. Okay, the frequency stays the same. Now really, there's a lot going on here. The reason that the frequency must stay the same is because if it didn't, then we'd have what's called a discontinuity. You imagine we have our wave oscillating right at this boundary, then the points either side of the boundary must oscillate with the same frequency, because otherwise there would be a discontinuous wave, and that would not make sense in our physical world. That's a really poor explanation. However, it is enough hopefully to convince you that the frequency is always constant. Okay, so I suppose another way of saying this is to know that whatever the wavelength does, the speed does too. If I have the wavelength, the speed will have as well. If I double the wavelength, the speed will double as well, and that's to maintain a constant frequency, which is why the answer here is A.